Welcome back to Pop Goes the Stack, the podcast where the future of tech shows up with big promises and no run book. I'm Lori MacVittie, and I'm here to read the fine print. So today, we wanted to talk about GPUs because everybody else is talking about GPUs, and they think that they're the bottleneck for getting performance and scale for inference. And guess what? It's not, actually. It's memory. And more specifically, it's the KV cache. It's quietly eating your lunch while everybody else is busy counting accelerators. Because here's the thing, inference stopped being stateless the minute we started doing real work with it. Long context, multi-turn conversations, agents that don't know how to quit, all that piles up state, and that state has to live somewhere. Now, right now, and too often, it's living in the most expensive place possible. So in this episode, we've got Tim Michels. Hi, Tim.
Oh, good morning, Lori.
Good morning. To dig into KV cache offload and other offloads, we're going to talk about a few different types to kind of understand what's going on. And we want to talk about it not as a cool optimization, but as the architectural shift it actually is. You know, what happens when you stop treating inference like a request pipeline and start treating it like a stateful system? Because if you don't, you're going to spend a lot of money recomputing yesterday's thoughts. Now, you'll notice Joel Moses is not here today, and that's because Joel Openclaw Moses is off in some kind of execution loop and couldn't make it. But he'll be back, don't worry. So it's just you and I, Tim, and let's dive in and start by kind of defining what the heck is KV cache? Everybody's talking about it. What is it actually?
Yeah, well, I think in order to understand KV cache, you have to get beyond this monolithic understanding of how an LLM actually functions and how it's built. So when you think about an LLM, you send it a prompt, it chews on the prompt a while, and it spits out a response. That's the monolithic view. But when you actually go a click down under the covers, it's actually a two-step process. So the prompt comes in and it gets chopped into tokens, and these tokens are processed, vectorized, labeled, however you want to think about it. And this creates the base data structures to then be fed into the second stage, which is the decode, which does a token by token response generation. But that middle thing, that the output of the prefill that goes into decode, is called the KV cache. And so that's the thing we're talking about. And if you have KV cache handy, you can skip the very expensive and slow prefill stage, which is taking prompt text and turning it into vectorized context for the LLM.
And that's helpful, especially as we start hearing people talk about distributed inference, where they're actually starting to break that up based on those divisions. So there's the prefill that fills up the KV cache that goes into decode and then gets churned on by the model.
Yeah, and right? An observation people have made that to take advantage of that separation is that prefill is computationally bound. It's very heavy in the number of flops required, as opposed to decode, which has to hold the entire KV cache context and operate on it. So it tends to be memory bound. So if you can have dissimilar heterogeneous compute, you can actually say, hey, these nodes with their GPUs are better. They're built for prefill, versus this pool of nodes is better and built for decode. And so you can actually get sort of a separation of concerns and target the right infrastructure for each job.
And that's good, because right now we all know that GPU memory specifically is very, very expensive and it's hard to get your hands on. Like there's at least that's what I think
there's two elements before I jump into the memory. Let's talk about the GPU part, which is, if you just send your prompt and it chooses a random, say a round robin GPU, when you get there, there's nothing, there's no context. You have to build everything from scratch. And this gives you the longest time to first token. This gives you the most consumption of GPU resources to get your response. But if you've been there before and you've essentially asked the same query, maybe it's the same query with a different detail added to it, what you really want to do is go back to that same GPU that already has your cache and start with that work already done. So the ability of a load balancing system to understand prompt to GPU assignment so that you're targeting GPUs that might have that cache still available to them, that's a really powerful tool. Now, how does that overcome your problem, right? You're saying, hey, this cache is in HBM memory. This is the smallest, most expensive piece of memory in the system. It's right there next to the GPU compute.
Mm-hmm.
The way we tackle that is creating a memory hierarchy. This idea that, yes, there's HBM memory. That's amazing, but it's small. Then there's the host memory of the host CPU that's holding that GPU, and it has a much bigger DRAM footprint than the HBM footprint. And then within that node, there's also a local SSD, which is probably measured in many terabytes of storage. And then behind that, we have a fourth tier, which is network attached storage, which can be measured in petabytes. Mm-hmm. Each of these is colder. Each of them is further away. Each of them is slower to get to. They are all faster than having to recompute.
Wow. And that's really what's going on, is we're trying to improve the performance and efficiency of these systems because, well, they're really expensive and users don't like to wait for a recipe for, apple crumble.
Yeah.
Like, I
can't
with
time to first token being one of the key measurements here.
Right. And the way that we've dealt with this through all of the application generations, if you will, we've always gone back to how can we offload or cache some information that will make it faster to do this, to avoid something that is computationally expensive, right? That's one of the reasons that, sticky sessions, works, is because the computational expense there is usually I have to actually negotiate the TCP and I have to open up a socket and there's IO and it's expensive. So let's just keep it open, right? We kind of cache the session in order to make it faster. And every time a new application type comes out, we see these problems like, this is really, taking a lot of time. How can we optimize it by caching or offloading? Now, KB cache is one way to do that, but you mentioned semantic caching earlier too as another option for how to actually make this faster. So can you explain that?
KB cache is getting into that middle step between the prefill and the decode within the LLM. An alternate view is I'm going to step outside the front door of the LLM. I'm going to observe prompts that go in, capture the replies that come back. And then I'm going to cache that as a semantic cache. If I see another prompt come in that matches something in my cache, I don't bother the LLM. I just respond immediately with the same response because it's the same prompt. So you assume the response has to be the same, right? So that's a really powerful technique for, leveraging your infrastructure to get much faster response times and much more effective compute.
I've often, you hear this, every time you say thank you, it's costing whoever is hosting that LLM, it's costing them millions because you say thank you. If there was an intermediary in there, it could just catch the thank you and respond appropriately and never actually incur the cost. Like, this seems to be like an obvious solution to me, but call me silly. Maybe I've been in that, app delivery intermediary world too much. I'm like, that makes sense, right? So similar, right? Yeah. Being able to intercept and reuse anytime. And part of the reason that we need to think about things like this is that the context windows have grown incredibly huge, and that gets sent back, and that's causing a lot of this problem, I guess you would say, in the KB cache, because if you have 1 million token context, right? I mean, that's huge. It's got to process that, right? If you send it back, or is only part of it recomputed? Now, so that's the other question. If I'm in the middle of writing a book with an LLM and it's got a lot of this already, how much of that is in the cache? Is it only the new stuff? Is it the old stuff? What's going on in there? Like, how much of that is actually causing the problem?
I think the size of the cache is a big problem. So there's some math that says an individual token in cache represents 500 kilobytes of data. That's one token. And so when we build out, say, an average prompt, we quickly get to a size of like 60 gigabytes for one prompt, 1 KV cache for one prompt. So even when you say, hey, this thing has filled up my HBM, I push it off to storage somewhere. Now I want to go get it, and I want to get it now, and I'm in a hurry. Oh, we got to stream a 60-byte storage query back to the GPU systems. The networks aren't necessarily built for these elephant flows, right? We're talking about a low number of queries, but massive transfers. And I think it's breaking networks and it's breaking storage arrays. Their TCP stacks aren't necessarily tuned for this. The intermediate middle boxes aren't tuned for this. There are problems that show up with these workload patterns.
I hear RDMA tossed around a lot as solving that back end problem. But then again, I've heard a lot of different, InfiniBand, this, that, right, on the back end to try and solve some of this.
Yeah, I think it's, there is some RDMA, but it's more of a traditional Ethernet networking problem. And in fact, companies like NVIDIA has come up with their NIXL NIXL, which is a networking library. I think it stands for NVIDIA Inference Transfer Library. And so this is their mechanism of having an optimized networking stack just for this problem. And so if you can get that stack running on the GPU side and on the storage side, you can get very efficient transfers between the two because it's been tuned for these large transfers.
Wow. Well, if it wasn't stateful, if you didn't care and you just answered every prompt cold, right? I mean, why do you need to know my entire history before you answer, right? And I mean, you do, right? The idea that these were going to be stateless
but your CFO won't like the
crazy.
answer. If your answer is buy more GPUs, your CFO won't like that answer.
No. Well, they don't like buy anything. You put buy in a sentence and they just immediately go, no, you can't have that. So there's other solutions. And one of them, and you mentioned this earlier, so now I want to come back to that, is the load balancing, right? The routing, right? As we're starting to look at it, because it's less about, it is load balancing, but it's more routing to the right model. And you're using different values. Like traditionally, we base it on what, how fast you responded, how many connections you have, what's your health, things like that. Location, you can do sovereignty, all sorts of things. But you're saying we actually need to start thinking about incorporating things like KV cache. What's the queue length? Variables that tell us, how efficient a particular model is going to be at processing this prompt and choose that instead. Yes?
Yeah, so if we go to a throwback story, right? Back in the day for web caching, it was about persistence for the shopping cart. So you open a session, you're shopping, you go away. When you come back, if you go to a different server, it knows nothing about your shopping experience. So you need to persist. Your new session needs to know, oh, this is Lori. She was just here 10 minutes ago. Let's take her back to her cart and show her the items she had already set up to buy. That kind of persistence is similar to the KV cache. You've been here before, you created some state, and now for a better user experience, we need to take you back to where that state is sitting, and that's typically near the GPU or AI cluster that you were on before.
That requires a little bit of, accounting, right? You have to keep track of which user went to which GPU or, which model, where is it likely to be? And that actually seems a little easier than keeping track of what's the state of the KV cache or the queue length in every single model instance. Is just like, hey, it's Lori. She was on number 1 before. Let's send her back there.
And you can see the similarity to semantic caching because you're sort of keeping track of the same keys, which is the prompt and the user. But now you're just keeping the location as the output of the cache, not the actual response.
Oh, so it's like sending it to a distributed cache, sort of like, almost like sharding, like, oh, this is A to M, it goes over here because that's,
yes.
Yeah. Oh, I caught that. I'm happy with myself this morning now because I caught that. But those are the kinds of techniques that we have to get to be able to deal with this, because it's not, even if GPUs and the memory associated with them are suddenly like, hey, it's a nickel, right? They're just easy to get and they're very, very cheap. You still have the problem of performance. That doesn't solve the performance issue and keeping context together. And that's really something for that app delivery tier, if you will, that routing to help manage, because the notion that these are going to be stateless is bunk, right? They are stateful in a sense, and we need to adapt to be able to optimize the entire right data flow, if you will.
Yeah, I think if you
Using
look at the arc of the AI infrastructure build out, it's been run and build as fast as we can, and there's no time for optimization. But as we start to run into the power wall, which means you don't have any more gigawatts, the space, you don't have any more data center space, and the dollars, you just run out of your trillions of dollars. We can't build more fast enough, so we have to turn back and say, hey, can we get a lot more performance out of what we've already built? And then I think we slow down and we start to look at these systems and start to tune them. And we'll discover there are 2x, 3x, 5x improvements we can make on our existing infrastructure. And a lot of that revolves around this idea of KV cache, location awareness, semantic caches. This is where we can get high leverage very quickly.
Cool. We need to get on that, because this isn't going away, and I think agents are going to exacerbate this problem, because now you've got, and they need to be fast, right? We expect them to be fast, at least, like, go do these things and do them quickly, because I'm waiting for the answer or a response. And you're going to have the same issues with them, but they're actually, at least as we assume at this point, they will be a one-to-many. One user might have many agents running around. So we're actually multiplying our impact on how much is being used. So we need to get really efficient and optimize how that actually happens.
Yeah, and the scale of all this is tremendous. If you're building, say, for a KV caching solution for 100,000 users, if you're in a hyperscaler use case, you're talking hundreds of petabytes of KV cache storage in order to run the 4-tier system, right? So how do we hook up all that networking? How do we make all of that work? These are interesting problems that the networking storage companies are only just now beginning to grapple with.
Yeah, and I mean, I hear about the distributed inference, and part of me goes, well, that makes sense. And it does, right? And especially as you described it, right? Being able to optimize for the resources and the hardware that you have, and build it out that way. But then we're introducing another network hop and another network, right, thing that we have to optimize, make sure it can handle the speed, the bandwidth, right? Everything. And every time we do that, we've seen us devolve into this, SOA microservices. There's just too many, right? We can't actually like call enough things fast enough. So I think there's a balance there to be very careful about as we start distributing this stuff, is that we can't distribute it too far yet, because the network still remains kind of, in some cases, a bottleneck, in that we can't move stuff. We can't move data through the system fast enough.
Yeah, I mean, that drives you to data locality. But again, this is a caching story, right? And let's move the prompt around, because it's much smaller than the KV cache.
I like that. Yes, move the small things. That's going to be my takeaway, right? Right now, that's the takeaway, right? Is, you move the smallest things, reuse, right, as much as you can, and store the small things.
And just the economics of this are going to drive incredible progress, because the most expensive thing by far is your GPU compute. So we need to be investing in storage and networking solutions and intelligence at the edge of these AI clusters to make the AI clusters more efficient, because that's where the money is. And we have, as we start to monetize this AI infrastructure, it's going to be all about efficiency, right? And TCO. And so, there will be money spent on storage and network efficiency solutions, because the payback of it is enormous.
Well, so if you were going to give a takeaway for the enterprise who isn't, right, they're not building these solutions, they're looking for those solutions, what can they do right now to help start being ready to optimize and make the most of what they do have? What can they do?
I think if they're building new infrastructure, they need to talk to their partners up front about efficiency solutions, and not just accept the answer of buy more GPUs. That's the wrong answer. If they already have GPUs, I think they can look into retrofitting on the outside to get more out of them. And there's been a lot of examples already in, the open community about how this is done, and the results have been very encouraging.
I like that. I mean, boiling that down, the answer is never throw more hardware at it. Like that's just, it's never the best answer. It is an answer. People do it, but it's never the best answer, and it's not going to be the most efficient. So, yeah, we're still figuring it out. I mean, that's the honest truth. We've got cache ideas, offloads, network. There's a lot of moving pieces here to get this as it starts to scale out. We're just starting to see the problems that we actually need to fix. So it's coming.
The encouraging thing, Lori, is we've solved a lot of these problems in other domains. We just need to bring those thoughts and solutions to this new domain, which is
right. Yeah, I think it is. We just needed to see that the problem exists and go, oh, now we need to solve that one. It's a little different. Let's do this. So we will solve it. And that's a good thing. That's a good thing. Not today, because that's a wrap for this episode of Pop Goes the Stack. If this episode helped you spot the next production headache early, subscribe before the change window closes.